Welcome to Orbital Dynamics Part 46. This part is based on excerpts from the book, The Mechanical Universe. How does potential energy arise? It occurs in fields of attractive or repulsive forces. Gravity is an attractive force. This is how we typically depict force lines. The density of the arrows represents the strength of the force. In this picture, it's not meant to be exact, just representative. This is one way of representing the 1 over r squared law. As you move away from the source of attraction, the field density diminishes. The field lines extend out to infinity. You'd measure a field with a test mass. It's better to use one that's significantly smaller than the field source. Otherwise, the test mass's gravitational force interacts with the central bodies. In mathematics, we use a hypothetical test mass. Another kind of a field is an electric field. If we change the central body from a mass to a positively charged particle, it sets up an electric field. If we place a negatively charged particle in the field, it will experience an attractive force. Electric fields are both attractive and repulsive. If we were to place a positively charged particle in this field, the arrows would go in the opposite direction. Here's an electric field with one positive and one negative charged particle. The charges are equal. The field lines end up looking like this. This is called a dipole. Another type of field is a magnetic field. With magnetism, polarity has to come in pairs. You have to have a north with a south. You can't have a single north pole. Magnetic and electric fields are both attractive and repulsive. Gravity is only attractive. Potential energy represents the ability to do work and, as we said in the last section, is force times displacement. Potential energy only exists within a field. Put a test mass or test particle in an area where there is no field and there's no potential. Put a test mass within proximity of another mass and the two will attract. From a distance, the mass has the potential to fall in. Likewise, put a charged particle in an electric field and it has potential to move either inward or outward. The same is true of a magnetic field. Where in the universe is there no potential? Nowhere, really. It's hypothetical. Gravitational fields extend out to infinity, so do electromagnetic fields. Since there's mass all over the universe, you might find an area where gravity is weak, but you never escape it entirely. With electric fields, you could conceivably create an environment where the charge is neutral, but since there are electric field differentials all over the universe, you also can't really escape electromagnetic fields. Here's an example of a ball rising and falling. It starts with kinetic energy that gets converted into potential energy and back again. Kinetic energy is imparted on the ball. It's thrown straight up. In fact, to accomplish this kind of motion, you'd have to fire it from a cannon. As it gains height, it gains potential energy. At the same time, since there's a downward force of gravity, it loses kinetic energy. At some point, at the apex, the ball loses all of its kinetic energy and for an instant doesn't move. With nothing but potential energy, it begins to fall back to the ground. Back at the ground level, the ball regains all of its kinetic energy that it started with. The velocity when it hits the ground is the same as the velocity at the start. In the last section, we derived equations for potential and kinetic energy. Several sections ago, we derived the equation for position. The position h equals the initial position p plus the initial velocity v times t, the time, plus 1/2 the acceleration times the time squared. This equation assumes straight line motion and constant acceleration. The example shown in the animation is straight line motion, and for now we'll assume constant acceleration. In our specific case, we're dealing with gravitational acceleration. Here we substitute g for the acceleration term a. G equals negative 9.81 meters per second squared. In this example, the initial velocity is 7 meters per second. Recall from the previous section that if we know the potential energy, we can derive the kinetic energy, and if we know the kinetic energy, we can derive the potential energy. Specifically, if we know the position, we can derive the velocity, and if we know the velocity, we can derive the position. Here's the formula for kinetic energy. At the start of this trajectory, the kinetic energy is greatest. If we want to know the total energy of the ball, we'd start with the potential, where the potential energy is 0. The velocity is 7 meters per second. Kinetic energy is thus 1/2 times the mass times 70 meters per second squared. That's 4,900 divided by 2 meters per second squared. And that's the mass in kilograms times 2,450 meters squared per second squared. Recall that the units of energy are kilograms and meters per second squared, which are joules. If we were to convert all of the kinetic energy into potential energy, we do that with this equation. Potential energy is m times g times h, which equals the negative of kinetic energy. We can cancel out the mass m. That leaves us with g times h equaling 2,450 meters squared per second squared. H thus equals minus 2,450 meters squared per second squared divided by g. G is minus 9.81 meters per second squared. If we do that division, we end up with h equaling 249.75 meters. The point where kinetic energy is 0 and where potential energy is at its maximum is at 249.75 meters. That's the apex of the ball's trajectory, which you can see in the animation. The ball peaked and came down to rest momentarily just below 250 meters. Let's figure how long it took for the ball to reach that height. The equation for height is here. If we plug in 249.75 for the height, 70 meters per second squared for the velocity, and minus 9.81 meters per second squared for the acceleration, we get this equation. If we solve for t in this equation, we get the time when the ball reaches its maximum height of 249.75 meters. This is a quadratic equation. We solve for t by first subtracting 249.76 meters from both sides of the equation. We also divide the acceleration by 2 to get minus 4.905 meters per second squared. Recall from algebra that this is a quadratic equation, and we solve for x with the quadratic formula. T thus equals minus 70 plus or minus the square root of 70 squared minus 4 times minus 4.905 times minus 249.75 over 2 times minus 4.905. 70 squared equals 4 times 4.905 times 249.75, so the term under the radical equals 0. The quadratic formula simplifies this. 70 divided by 9.81 equals 7.136 seconds. That's how long it takes for the ball to reach its apex. 70 meters per second is the velocity. 9.81 meters per second squared is the acceleration. All we've done here is take the negative of the velocity divided by the acceleration to get the time it takes for the ball to reach its apex. These formulas are fine for a constant velocity. Gravity, however, diminishes as the distance from the center of mass increases. Recall that it diminishes by 1 over r squared, where r is the distance from the center of mass. These equations work pretty well for trajectories near the surface of the Earth. They don't work when the distances get larger. In the previous section, we defined work as force times displacement. Near the surface of the Earth, the gravitational force equals mass times g. Work and potential energy thus equals mgh. In section 2, we introduced Newton's universal law of gravitation, which states force equals minus g times m1 m2 over r squared. G equals 6.693 times 10 to the minus 11th. If we assume m2 is much smaller than m1, then F equals ma. m2a equals minus g m1 m2 over r squared. The m2's cancel, and we're left with an equation for acceleration. The mean radius of the Earth is 6.383 times 10 to the 6 meters. I adjusted this number to make the final result come out to 9.81. As I said in section 44, the radius of the Earth varies depending on where you are, as does g. So we'll go with 6.383 times 10 to the 6th. The mass of the Earth is 5.95 times 10 to the 24th kilograms. If we plug in those numbers, we get 9.81 meters per second squared for acceleration. If we're 250 meters above the surface of the Earth, the acceleration goes down by about 0.001 meters per second squared. Not enough to notice unless you're measuring very precisely. Go up to 1,000 kilometers above the surface, however, and the acceleration drops appreciably to 7.33 meters per second squared. In the denominator of this equation, we have the radius of the Earth plus 10 times 10 to the 6th 10 times 10 to the 6 meters is 1,000 kilometers. To account for altitude, or distance from the center of the Earth, we express potential energy this way. Recall that in the last section, we set an arbitrary point for potential energy. If we consider the Earth a point mass, the potential energy point could be the center of mass, but the convention is to do just the opposite. The 0 point for potential energy is far, far away from the center of mass. Specifically, it's at infinity. That means the potential energy in a gravitational field will be a negative number. If the reference point were at the center of mass, the formula for potential energy would yield a very large number. Since we're interested in comparing potential energies at different locations, smaller negative numbers are easier to deal with. Since our reference point is no longer at the surface of the Earth, we use r rather than h. Potential energy is mr times minus g times the mass of the Earth over r squared. There's an r in the numerator and an r squared in the denominator. We can take out the r on top and one of the r's on the bottom. Potential energy is thus minus g times m times the mass of the Earth over the distance from the center of mass. Kinetic energy is always 1/2 mv squared. The equation for height would be p, the initial position, plus v, the initial velocity times t, plus 1/2 minus g times the mass of the Earth over r squared times t squared. Here's the equation for velocity. It makes use of this equation and substitutes gm Earth over r squared for g and r for h. Velocity is the square root of 2gm Earth over r. Here's the equation for height. It makes use of this equation and substitutes gm Earth over r squared for g in the denominator. It simplifies to v squared r squared over 2gm Earth. And here's the equation for the time to reach the apex. It makes use of this equation and substitutes gm Earth over r squared for a. It simplifies to vr squared over gm Earth. We can derive these equations with integral calculus. Let's calculate the work done in sending a rocket from the surface of the Earth, where r equals the radius of the Earth, to some distance r sub f far away. First, we must apply a force, F sub rocket, equal and opposite to the force of gravity. The force of gravity is given here. For simplicity, let's assume the rocket is launched straight out on a spherical Earth that's not rotating. The force, F sub rocket, and displacement will be in the same direction. Since this is linear motion, the work done by the rocket is the integral from the surface of the Earth, where r equals the Earth's radius, to our point far, far out in space, r sub f. The force of the rocket counteracts the force of gravity, and that equals g times m times the mass of the Earth divided by r squared. We'll make that substitution. G, the gravitational constant, m, the mass of the rocket, and the mass of the Earth are all constant. They can be brought outside the integral. We're left with the integral from the surface of the Earth to the far out point, r sub f, of 1 over r squared dr. Recall that to turn an integral into a formula, we need to determine the antiderivative of the function, 1 over r squared in this case. In part 28, we went over some elementary calculus. We show that the derivative of x squared is 2x. In general, the derivative of x is x to the n, is n times x to the n minus 1. 1 over r is same as r to the minus 1. The derivative of r to the minus 1 is minus 1 times x to the minus 1 minus 1. That equals minus x to the minus 2, which is the same as 1 over x squared, as minus 1 over x squared. So the antiderivative of 1 over r squared is minus 1 over r. To solve the integral, we evaluate minus 1 over r from the radius of the Earth to the distant location r sub f. That equates to minus 1 over r sub f minus a minus 1 over the radius of the Earth. That simplifies to 1 over the radius of the Earth minus 1 over the distance to the distant location. That equals gm m Earth over r Earth minus gm m Earth over r sub f. The potential energy at the surface of the Earth is minus gm m Earth over the radius of the Earth. The potential energy at the distant point is minus gm times the mass of the Earth over the distance to the far point. In general, the potential energy is minus g times mass m times the mass of the Earth over the distance from the center. Notice that as r goes to infinity, the potential energy goes to 0. Let's say we wanted to know the velocity at the surface of the Earth that the rocket would have to travel to escape completely from the Earth's gravity. In that case, we'd set the outer radius r sub f to infinity. If r sub f is infinity, then 1 over r sub f is 0. The kinetic energy required would equal the change in potential energy. Since 1 over infinity is 0, this simplifies to this. We can multiply both sides by 2 and cancel out the mass m in both sides of the equation. The escape velocity is the square root of 2 times g times m Earth over the radius of the Earth. Plugging in terms, we get this equation, which equals 11.19 kilometers per second. Here's an animation where we don't quite reach escape velocity. The initial velocity is less than 11.19 kilometers per second. The graph on the bottom is the acceleration. Notice how it declines at the apex and then increases when the ball reaches the ground. This is because gravity diminishes with the distance from the center of mass of the Earth. Here the ball reaches escape velocity. The scale on the left is much larger. The plot in the middle is acceleration, and the one on the bottom is velocity. Notice how rapidly the acceleration drops off. As the ball gets farther and farther from Earth, the acceleration goes quickly to 0. Notice how the velocity changes too. The ball is never coming back to Earth. That's what escape velocity implies. The velocity, however, gets slower and slower. If I could show you the ball at infinity, you would see it come to rest and never fall back. The ball travels from the surface of the Earth at a faster velocity. If the ball travels from the surface of the Earth at a faster velocity than the 11.19 kilometers per second escape velocity, it would keep going, and as Buzz Lightyear might say, to infinity and beyond. This gives you some sense of the kinematics of objects traveling away from a gravitational field. A common analogy is a gravity well. It uses a constant downward gravity and an object moving horizontally to explain three-dimensional gravity that diminishes over distance. While it's a flawed analogy, it does give you some feel for how objects interact with a gravitational field. Look at the acceleration plot and imagine a ball that's rolled up its ramp. Or look at the acceleration plot and imagine that it's a ramp. Now imagine you roll a ball up the ramp. If the ball does not have enough velocity, it will only roll partway up the ramp and then back down. Given enough initial velocity, it will make it over the hump. From there, it only needs a small amount of inertia to carry it to infinity. As you get farther away from the source of gravity, the curve gets nearly horizontal. The near horizontal part doesn't get completely horizontal until the ball reaches infinity. So for eternity, the ball will be rolling uphill at an ever so slight slope back downwards. Here we've taken into account the escape velocity of the Earth. The Earth, however, orbits around the Sun. A ball starting at the Earth would need to be going 42.18 kilometers per second to escape the gravitational force of the Sun. If we look to the galaxy, the ball has to escape the gravitational force of the Milky Way. For that, it requires speeds between 500 and 600 kilometers per second. You can see why in our local galaxy there is no inertial frame of reference. The same holds true for the entire universe. You'll recall in Part 18 we developed equations for the proper motion of a planet or satellite in orbit around a central body. The velocity at apoapsis is slower than at periapsis. Since there is no net force acting on the orbiting body outside of the gravitational force from the central body, the energy of the orbiting body must be conserved. U plus k must equal a constant. In the case of potential energy, U equals minus g m over r, where little m is the mass of the satellite, and big M is the mass of the central body. We're assuming here that big M is much larger than little m. As the distance from the central body increases, like at apoapsis, the potential energy increases. As r gets larger, 1 over r gets smaller. Since u here is a negative number, a smaller value represents an increase in potential energy. Likewise, as the distance from the central body decreases, like at periapsis, the potential energy decreases. The kinetic energy must increase to compensate. Thus, the satellite must move faster. In the animation, as the satellite gets near the Earth, the velocity has to increase to account for the loss of potential energy. The kinetic energy increases with the velocity squared. Looked at the other way, the velocity squared increases so that it accounts for the loss of potential energy. The same happens at apoapsis. We'll delve more into this later when we characterize the energy of an orbit.